like to copy the state of a spin half system. So the two orthogonal states, I'm just denoting 0 and 1. And what are you looking for then? More or less you are looking for a unitary transformation which transforms, let's say, your spin down state, which I call 0. And of course you need a second quantum system which represents something like the empty paper where you put the copy on. And maybe there's a third part of the whole quantum system which represents the machine, if you want, the copy machine. So you're looking for a unitary transformation which copies a spin down state with a certain preparation of the paper and the machine into two spin down states. Now here the paper state is replaced by the spin down, and of course the machine state ends up in some state, let's call it A0. And let's assume you are able to construct such a unitary transformation which succeeds in copying two orthogonal states, 0 and 1. And so for the one state, this would be the desired picture. Now, there's no fundamental restriction which forbids quantum mechanics that can be done. But you immediately see, because any unitary transformation, or even if it's anti-unitary, has to be linear, you will not be able to copy an arbitrary superposition of these two states. Why? Because just assume that this is possible, and then you apply the linearity, and you end up with this state here. But what you really want would be this state in the second line. And of course, these two are only identical if alpha times beta is 0. And so if both coefficients here are non-zero, it's not possible. So this is the main idea of this so-called no cloning or no copying property of quantum states. And this has been emphasized very much by Šurek and also by Wutos. And it gives you already a hint that if you want to use quantum states for storing information, that this is a different thing than classical information, because classical information can be copied arbitrarily. Now we see here that it's the linearity of quantum mechanics which imposes or which implies this no-go theorem. Now let us see a little bit what can quantum mechanics do in this respect if we want to copy such an arbitrary spin 1/2 particle state. So let's just consider one particular quantum process. So let's imagine that our initial spin 1/2 particle, which we want to copy, is in a pure state. And we will now, as coordinates of these pure states, we will take now a Bloch vector M, which identifies more or less in which direction this spin is pointing. And we assume now we do no longer consider the machine, but we consider only the empty paper. And the empty paper state, we assume it's completely unpolarized. And then let's consider a particular quantum process, which I just pick at random. And this would be a process where we just measure the total angular momentum of the two spins. So here we have a spin 1/2 particle and here. So the total angular momentum can assume the values 0 and 1. And this would be the mapping of such a measurement process. Now if we are lucky and we find the complete system in a total spin 1 state, and if we work out the details, then we find that this is really the state which results from that. So we get, of course, both states have j equal 1, but there is one component which has a magnetic quantum number of 1 in the same quantization axis as here, this state, and of course there's an m equals 0 component, and this is a mixed state. And we get this, and actually this would be the desired state, because it really is a state where both spin 1/2 particles now point in the same direction. But we are able to obtain this state only with a probability of 2/3, and not with 1, which would be for a perfect process, but perfectly it's impossible. Now, this process here has a very remarkable property, because this probability of success of 2/3 remains always the same, irrespective of the quantization axis which I use for this input state M. And written out mathematically, it's just this statement. If I take instead of my initial state, let's call it M0, an arbitrary state M, which is which I can always obtain by an arbitrary unitary transformation from this M0. In the case of a spin 1/2 particle, it would be just a rotation, as an operation of the member of the group SU2. Then the output state of this state M is just obtained, is related to the output state with the quantization axis M0, just also by a rotation. But now I have to rotate two particles. And this property I call covariance property. So if we are interested in a technical question, because we know copying is not possible perfectly, how good can we do it? And if we succeed, we want to do it, of course, for all possible input states with the same success probability, then we better concentrate on this type of quantum processes. Now, there's an additional thing here in this simple example. If you concentrate on the measurement result where you observe a total spin of 0, then your output state is just the state with angular momentum 0. It's the totally antisymmetric state. And of course, this is rotational invariant. That means this process would then always generate the same state, irrespective what the input state M was, really. And it's antisymmetric, so let's keep in mind. Now, this is the motivation for studying so-called covariant quantum processes, which are more or less determined by this property. And so, in the rest of my talk, I would like to study these processes. This covariance property is a certain symmetry property, because the success probabilities of such a covariant process should not depend on which input state you are really using. And so the question I'm interested in answering is, what are the limitations imposed by quantum mechanics, also by the linearity, and the fact that you always have to have a mapping of a positive operator onto a positive one on these particular covariant quantum processes? What is the most general structure of the resulting output state? How do they depend on the dimensionality? So far I've only discussed two spin 1/2 particles, and I would like to answer that for arbitrary dimensions. And of course, I would like to discuss a little bit the covariant copying processes, the optimal one, and processes which entangle two states. Also this example where you project onto the state with total j equals 0 was an example of an entanglement process. You add one particle, you put two particles together, one in a reference state and the other one in an arbitrary state, and as an output you get an entangled state, irrespective, with the same probability, irrespective which state you chose for your starting state. So what are we looking for? Let's make this a little bit more precise. So what we would like to study is quantum processes of the kind where we have a first quantum system prepared in a pure state, which I just labeled by coordinates m. You can think of this m just as the Bloch vector. Of course, you can generalize this concept to an arbitrary dimensional state. And the second quantum system is assumed to be of equal dimension, but it's prepared in a known and fixed reference state. And now I'm looking for quantum operations which produce two particle output states which have the following property. If I take an input state, a pure input state M0 for the first system, and then I get a certain picture, a certain result for this quantum state. If I take another input state, pure input state M, which I can always relate to this previous one by an arbitrary unitary transformation, this process will give me another picture, another output state. And now the symmetry, the covariance conditions implies that there is a direct mapping. The direct mapping between these two output states is obtained by this relation. This is the symmetry I'm looking for. Now, of course, any quantum process has to be a linear mapping between density operators. This is one of the very fundamental laws of quantum mechanics. And it has to be positive. That means any positive operator, a density matrix is always a positive operator, has to be mapped again onto a positive one. Now let us briefly outline a little bit how this construction of these covariant quantum processes can really be done for arbitrary dimensional quantum systems. And we will end up with the somehow surprising result that if you impose this covariance constraint, you only need 5 real parameters which can classify all these processes. Now, what we do first, we have to somehow parameterize the most general possible input state. And of course, if I have a d-dimensional quantum system, I can write the most general input state in a form which is similar, which you might be familiar of also from the spin 1/2 particles. So I can always write it as a linear superposition of the unit operator plus some linear combinations of generators of the group SU in d dimensions. For example, take the 2-dimensional case you are familiar with, then we know that for these operators here, we can always choose the Pauli matrices or linear combinations thereof. And of course, the M would then be nothing else than the Bloch vector. And of course, this concept you can carry over to arbitrary dimensions. The only difference is that the Pauli matrices, which would stand here in the case of spin 1/2 particles, they are replaced by the generators of the group SUD. Now, of course, if I impose the requirement that the input state has to be, first of all, the density matrix of the input state always has to be Hermitian, so you get some constraints on these components of the generalized Bloch vector if you want, and if it has to be pure, you also get constraints in the in the case of the spin 1/2 particle, you have the constraint that the M has to be a vector on the surface of a unit sphere. Now, of course, what is the most general 2-particle output state which you can get? You just take the same operators as a basis for expanding the most general output state. So you have a tensor product of 2 unit operators. Here you can have, of course, your generators of SUD and the unit operator, here the other type. And of course, you can have 2 products of generators of the SUD. And I would like to mention, of course, that I used here the summation, Einstein summation convention, that you have to sum over all indices which appear twice. This would be the most general 2-particle output state. And now, of course, any quantum process has to be a linear mapping between density operators, and we would like to be, and we are interested in particular in a certain symmetry property, namely this covariance. Now, because it has to be a linear process, these functions here have to be linear functions of M, actually. And if we impose the covariance constraint, I do not want to go into the details, but then it turns out very simply that this function here, this arbitrary function of M, just has to be proportional to this generalized Bloch vector, which defines your initial state, multiplied with a scaling factor. This is understandable because this covariance condition, more or less, you know that at least for spin 1/2 particles, these Pauli matrices transform like vectors. And so, in order to fulfill the covariance condition, you also have, as the covariance condition implies then, that here this function cannot contain any constant, but only a quantity m, which also transforms like a vector. And now here, this is the more tricky part. It turns out that if you impose the covariance condition onto this part here of the 2-particle output state, only certain sums of generators of the SUD are left. And you can understand this result easily in the case of the 2 spin 1/2 particles. This would just be a scalar. And this would be a combination which transforms like a vector in the SU2. And now, of course, you can carry this concept over to arbitrary dimensions, and it's very similar. The point is now the following. You have 2 real-valued parameters here, because this output state also has to be a Hermitian operator, so you get certain constraints on the m's. So the alpha you have 2 alphas here, one here, and one here. So these are 2 real parameters. The C can be complex, and the beta can be complex. So you have 5 real-valued parameters, which really parameterize more or less all possible output states, which can be obtained from a covariant and linear quantum process. And now comes the most difficult part. We have to make sure that the output state is always a density operator. That means a positive operator. All its eigenvalues have to be positive. And this part is complicated because more or less we have to determine all its eigenvalues and make sure that all of them are non-negative. And it turns out, because of this symmetry this process has, can be done analytically, and actually we have a very simple structure of these output states. So let's look at these output states in a little bit more detail. Without loss, because of this covariance condition which we impose, the symmetry condition on the quantum process, in order to answer the question under which conditions or which are the constraints on these 5 parameters under which the output state is also a state, a quantum state, that means a positive operator, we can restrict ourselves without loss of generality to one particular input state, because any other one can be obtained by unitary transformation. And this covariance condition implies that the spectrum of the output operator is not changed. It's invariant. So we just take one particular input state. Again, in the spin 1/2 case, it's clear. That means just without loss of generality, we just pick out one quantization axis. And then it turns out that the output state, because of this covariance, can be really written as a direct product of 4 types of density matrices. That means more or less in a matrix notation it becomes block diagonal. And the first density operator is just identical to the input state. Only it's a 2-particle state. It's aligned along the same direction. So if we are looking for an optimal quantum copying process, we would have to make the probability P1, which is multiplying this state, as large as possible. Then the other density operator is just a mixture of all possible other states of the form JJ in the basis. I just label my basis in this d-dimensional Hilbert space from 1 up to d. And then we have these 2 other states, rho 2 and rho 4, and they have a more complicated structure. Just let us note, in rho 2, always, at least in one particle, the input state appears. And in the other state, rho 4, it never appears. And of course, we can work out how these probabilities P depend on our 5 fundamental parameters which we have. And so, of course, for rho out to be positive, it's not enough that we just require that these probabilities are non-negative. We really have to determine the eigenvalues. And if we increase the dimension, of course, the dimension of these matrices gets larger and larger. But it turns out that these constraints coming from the fact that you obtain an output state, as a physical state again, are very easy to solve. We just get more or less these 5 type of constraints. One of the eigenvalues is P1, that's clear. That was obvious because that was just the state I called rho 1. So P1 has to be non-negative. Then we get a condition on the probability P2. And in order that this is not negative, we have to make sure that this part here is always larger than the square root here. Then P3 has to be non-negative. And of course, we have to fulfill these conditions. And now it's, for example, just to give you an idea, it's very simple to work out now, because we have the conservation of the probabilities of these 4 submatrices which appear. Now, it turns out, of course, the probability for this to obtain an output state P1, which would just be a copy, a perfect copy of the original input state, it's always by conservation of probability. It's related to the other probabilities by this. And you can bound it from above by a quantity 2 over the dimension plus 1. And you see here again, if the dimension of the system is 2, we get 2 over 3. 2 over 3 was this miraculous factor which appeared in this simple measurement process which I showed you in the very beginning, where you just measured the total angular momentum. So actually, and it turns out, if you want to make the copying as big as possible, this is what you can get, the best you can get. If you increase the dimension, of course, it becomes less and less effective. Now, so far to the quantum copying. In principle now, with these constraints, we have now an overview over all possible quantum processes which are possible, which fulfill this symmetry condition. And for example, just to give you a picture a little bit, a pictorial representation, I show you here an overview over the range of definition of the parameters. Of course, I have 5 parameters, so I cannot go into a 5-dimensional space. So I just fix 2 of the parameters, and I chose here, I show 3 independent parameters which you can vary, which are, for example, these partial probabilities for these density matrices. And we see it has the form of a tetrahedron, this range of definition. And for example, the optimum copying process would be just correspond to this point here. And now I would just briefly like to address the question, if we want to obtain entangled state, maximally entangled state with such type of processes, what are these processes? Of course, in order to answer these questions, we have to define a measure of entanglement. And there have been various proposals to define such measures. And one measure, which has been proposed recently by Vidal and Werner, is the so-called negativity. The negativity is the following. You just take the density operator of your 2 particles, and you transpose the indices of the second particle only, and then determine the eigenvalues of this new matrix. And this operation is called partial transposition, because you just transpose let's say, the part of the density matrix which refers to the second particle. And now, if it turns out, if this partial transpose has a negative eigenvalue, Perez has shown that then this state is not separable, it's entangled. And so one measure of entanglement is just taking the sum of all possible negative eigenvalues which you obtain from this partial transpose. And this has a nice property. One can show that this is a convex function. And because it's a convex function, if you have a certain range of definitions for your probabilities here, a convex function assumes its maximum always at the end of the intervals. And so more or less, our guess is that if we know the range of definition of parameters, which is a tetrahedron, we just have to look at the edges and the surfaces, and somewhere there must be the optimally entangled states. And actually, you can work out how they look like. And it turns out that it depends a little bit on the dimension. First of all, this state which would imply an optimal copying process has to be absent. And also the other states here which are separable. And so only 2 density operators are left, rho 2 and rho 4. And of course, depending on the dimension, either the probability of rho 4 is 1 or the probability of rho 2 is 1. So let me just give you an example of such optimal entanglement processes which come out from this analysis. Of course, for 2 dimensions, we already realized we had this measurement process, and it turns out an optimal entanglement process would always produce an antisymmetric state which involves just the 2 basis states. I just use this notation, an antisymmetric state formed by the states 1 and 2. And an antisymmetric state you can picture just as characterizing a plane, because it's a totally antisymmetric 2 forms, and this usually characterizes a plane. Now it's very interesting in 3 dimensions. For example, an optimal entangled state which would be the following. If, let's say, the state 1 is your input state, you get more or less the totally antisymmetric state which defines the plane orthogonal to this input state. And so this way you would also keep information about the orientation of your initial state, because this plane is always orthogonal to the other 2 states. So my time is almost at an end, so I would like to stop here and just summarize once more that essentially this classic treatment of in Fano's papers on quantum states, where he investigated general properties of density operators, which are the most general description of quantum states. If you just alter the question a little bit and concentrate on possible transformations between quantum states, you enter a fascinating regime where you really see that, let's say, the entanglement, I would almost say, between these three concepts, the symmetry which you impose on the process, the linearity, and the positivity, really tell you a lot about what quantum mechanics can do and what it can't do. And this question is, of course, of very central interest now in this field of quantum information processing. And I think in this sense, in Fano's review article, there's already a seed which you could consider also as being present in nowadays investigations in quantum information. Thank you for your attention.